Okay, so today I'm going to be talking about essentially what have we learned from nearby clusters using multi-wavelength observations. And to start off, I just want to say I'm Julie Hlavacek-Larrondo. I'm a professor at the University of Montreal. Okay, so let's get started. So when I first started thinking about this talk, I decided to write down all the topics that I wanted to talk about that focus really on multi-wavelength studies of nearby clusters. And this is what I came up with in about 2 minutes. So lots of interesting topics. I would love to review all of these, but for lack of time, I decided to focus on what have we learned of nearby clusters, especially those that are relaxed, because this morning we heard a lot about merging clusters. So I'll be particularly focusing on these 4 highlighted topics in black here. And I'm going to start off with one of the most important topics that we've learned about in nearby clusters, which is essentially AGN feedback. So these clusters have been really fundamental in understanding how this kind of feedback works. And to give you an example here, I've decided to show you a little bit of the history behind AGN feedback in clusters. So maybe some 20, 30 years ago, when we started looking at clusters, this is a very classical example, Hydra A. You see the dominant central galaxy here, the brightest cluster galaxy. So 20, 30 years ago, we knew that a lot of these central galaxies had very powerful radio sources. So lots of them had these powerful radio jets. And we knew also that clusters had a lot of hot intra-cluster gas, but we didn't really know that this gas would turn up to have so many really beautiful features that are directly related to this kind of feedback. And this field really kind of exploded when Chandra was launched and started taking images of these nearby clusters and really revealed that AGN feedback is a fundamental and important process in massive galaxies. And so it did this, for example, here you see the Chandra image of Hydra A. This was the first image taken in 1999. So what's happening is that you have the brightest cluster galaxy, you have supermassive black hole. This black hole is generating jets of relativistic plasma that plow through the intracluster medium. And when doing this, it actually pushes the intracluster medium. And so it's doing direct work against its environment. And this really provides a unique tool to understand what supermassive black holes can do to their environment and their galaxies. And so since then, there have been many, many studies that have looked at AGN feedback in clusters. Whether in clusters, in groups, or even individual massive galaxies. And what these studies have shown overall is that this kind of feedback, also called jet mode or mechanical feedback, is really a fundamental process in all massive galaxies, in the sense that if you have a galaxy, if it has a supermassive black hole that's accreting material and generating a jet, this jet is going to have a profound impact on its surrounding. It's going to inject a lot of energy. It's going to heat up the medium so much that it's going to prevent a lot of star formation in these galaxies. And so the typical example I give is that galaxies would be about maybe 10 to 100 times more massive if there was no feedback occurring. So this feedback really transforms galaxies at its core. So besides the energy it's injecting, one of the key questions that we've been asking ourselves concerning nearby clusters is how does this energy get propagated throughout the cluster core? And it's still unclear how this feedback occurs, but what we do know is that in one of the forms is these jets can generate shock fronts. We do see them in very nearby clusters with very deep observations. They tend to be very low Mach number shocks. So this is one mechanism that's very efficient at transferring energy from the cavities throughout the intracluster medium. More recently, there have been other studies that have been arguing that at larger scales, this energy gets transferred through sound waves and or turbulence throughout the medium. And I'll come back to this turbulence later on. One other really interesting result that has come up in the last couple of years is looking at nearby cool core clusters that have this feedback occurring. This is one example here, Able 2597, very well studied system. And one of the key features is that now with not only X-ray observations, but with the advent of ALMA, ALMA has been really fundamental in showing that jets can also generate outflows of molecular gas. And so this is really interesting because until recently, we thought that quasars were the only ones that could actually do this, so drive molecular outflows. But it turns out that black holes that accrete much less and that drive jets can also do this and really move around a lot of the gas in the cluster core. So you may wonder, is this feedback only occurring in the most nearby clusters? It turns out that we now have observations that have traced out this kind of feedback occurring in clusters out to relatively high redshift. So this is a phenomenon, this kind of feedback is happening on long time scales. We're talking out to about a redshift of 1. So for the last 8 gig years. So it's not something that's just happening now, but it does occur over long time scales. And so it really shapes the entire cluster core for a lot of the existence of the cluster. If you're curious, we're now starting to see evidence that black hole feedback may not work as well at very high redshifts. So when clusters were first forming at about a redshift of 2. If you're curious, I invite you to listen to Rhea's talk on Friday on this topic. But to move on, I've been in this field essentially for about 10 years. So we've seen what we've been able to learn about feedback, the overall general results of how it works in clusters. And there are really 3 lessons that I've learned from studying this field for the last 10 years. And the first 2, which are really important, is we can learn so much from nearby clusters, especially when getting very deep observations, because this allows us to probe a realm of physics that is much more detailed. And so just going deep on nearby clusters has really proven to show a lot of key results on feedback, but also many other topics. Of course, there's the multi-wavelength studies, which combining different telescopes, different wavelengths, we can learn a lot about fundamental processes. So I'm going to talk a little bit more about this for the rest of the talk. I'm going to highlight here some examples. So you can there's so many different techniques that we can use. If we look at cool core clusters, we can combine X-rays and radio observations of large scale structures. So there's been a lot of studies on radio mini halos in clusters, which have revealed a tight connection between the non-thermal gas and the thermal gas in clusters. You can go out to emerging clusters as well. And there's such a fundamental connection between these relics and the hot X-ray gas. So we've heard a little bit about this earlier this morning. Combining optical techniques to trace out the lensing properties and dark matter properties versus the X-ray gas. So again, very important physics that have come out by combining these different techniques. And other topics really interesting, jellyfish galaxies. I'm not going to talk about this topic because we'll hear about it in the talk right after by Florence. So stay tuned for that. And for the rest of the talk, I decided to focus more on the cluster cores of relaxed clusters and to show you what we can see from multi-wavelength observations. And there's one science topic that really pops out when you do this. So if I take this example, classical nearby cluster that has been extensively studied, the Perseus cluster, this is its brightest cluster galaxy. So it looks like, a very boring galaxy in this image. There's some kind of structure here, which is actually an infalling galaxy in the cluster. But what's really interesting, and this became apparent maybe 30, 40 years ago, when they started taking images, but at different wavelengths. And if you take the example of H alpha, this is what the cluster looks like with an H alpha image overlaid on top. So you see that the central region is completely different. These are called filaments, nebula that are found very often in cool core clusters at the center. They're associated with the brightest cluster galaxy. And so brightest cluster galaxies in these relaxed clusters light up in H alpha. So we're talking often about 10 to the 41, 42 ergs per second of H alpha emission. So very, very bright. And what's interesting is that most of these filaments here, although they're H alpha luminous, they are not star forming. And so a lot of people have been trying to understand how these filaments form and how they're connected to the cluster. So there have been many, many studies. I'm just showing here some examples of filaments that have been studied in nearby core clusters. So there's lots of work by many people that are here today as well. There are upcoming posters that are going to talk about these filaments, which are essentially, as I'll show, multi-phase nebula in these clusters. And so these filaments trace out not only the H alpha gas, which is 10,000 degrees, but it's directly correlated to many phases at different temperatures. To show this a little bit better, let's look at, again, the Perseus cluster, a beautiful example of a nearby system which has been extensively studied. So this is an H alpha continuum map. You have the brightest cluster galaxy here. This nebula of filaments here extends to about 90 kiloparsecs, or 4 arc minutes in the sky. There have been other studies that have tried to look at the kinematics of these filaments. And I just want to show you one of the little problems that we have with nearby clusters. Nearby clusters are fantastic for understanding detailed physics. The downside is that the field of view of instruments is quite limited. And so often it's very difficult to study these nearby clusters for that reason. But of course, there have been other, beautiful studies that have looked at the kinematics to try and understand, what's going on with these filaments, how are they formed, and lots of really great work, and how are they connected to the hot X-ray gas and the cold molecular phase. So this was in previous studies, this is what we were able to do. So Nina's worked a lot on this in the past, looking really at the kinematics and the complex kinematics of the core or the outer filaments. Now, with the advent of some of the new instruments, we've been able to do this in much more detail. And so I'm going to talk about one instrument which has really played a key role for understanding these filaments in nearby clusters. So this is CITEL. CITEL is an integral field spectroscopy, which essentially has a field of view of 11 arc minutes by 11 arc minutes. So extremely large. The entire nebula in Perseus, even though it's 4 arc minutes wide, fits in this field of view. And so you can get really the kinematics of the entire structure. And this is what it looks like. So if we look at essentially what's going on with these filaments, you see this is an image showing the velocity structure, so kilometers per second here, of the entire nebula. The central black hole is located at the central region here. And what's really remarkable is that when you start comparing what's happening with the H alpha gas, which traces gas at 10,000 degrees, versus the colder phases, you can do this with Herschel. And so this is the C2 emission and the kinematics of this emission. And I've highlighted here in green some regions that are the same. And you can see that the velocities are very, very similar between the 10,000 degree gas and the 100 Kelvin gas. So these two phases are really linked to one another. I'm going to highlight our more recent study, which has looked at the connection between the 10,000 degree gas and the X-ray gas. And it shows that, again, everything is connected between the hot 10 million degree gas down to the H alpha, down to the cold molecular phase. And so this is a study that was done by Lee et al. In 2020. And so what they did was they looked at 3 nearby clusters, Perseus, Virgo, Able 2597. And what they decided to do was to look at these filaments in these 3 individual clusters. And so I'm taking here the example of Perseus, but if you're curious, you can go see the paper for the other plots. And so what you can do is, once you have these filaments in H alpha, you can plot what we call a velocity structure function. So this seems like a very complex plot, but it's actually quite simple. So what you do is you take two different pixels, for example, at two different positions, you calculate the separation, the projected separation between these two pixels. And then what you do is you calculate the velocity difference between those two pixels. And then you plot the average velocity difference versus different separations. So we're going from about 1 kiloparsec, 10 kiloparsecs, and higher. And what this does is that when you plot this, it measures the amount of turbulence that you have in these filaments as a function of scale. And when you plot this, the first thing that's really apparent is that this line here, these lines are essentially, they have a power law shape, which is really reminiscent and indicates that the dominant motions here are turbulent. Okay, so it's turbulent motions that are that explain the velocity structure of these filaments. The second thing to notice is that when you get to about a scale of 10 kiloparsecs, something happens, something breaks in this relation here. And in particular, if you look at the inner region, so within the 12 kiloparsec region, so it's about this circle here, what happens is this break, there's a really strong break here, traced out by a red curve of about 10 kiloparsecs, and this directly indicates that the main driver of turbulence is on a scale of about 10 kiloparsecs where it breaks, and this coincides perfectly with the scale of the inner cavities, so the radial jets that are coming out from this AGN. So this links the turbulent motion to the AGN jets and argues in favor that essentially the turbulent motions that are being that occur in cluster cores are mainly driven by the central AGN. Even more interesting is if you compare the X-ray data. So if I take here, for example, in purple, the Chandra line here, this traces the turbulent motion as traced from the hot X-ray gas. And it's remarkable how it correlates perfectly well with the turbulent motion of the filaments. Again, connecting that the motions of the optical filaments are directly linked to the motions of the X-ray gas. So this is essentially what some of the studies that we've been able to do for nearby clusters and learn a lot about feedback processes. I want to finish with the future. And I think that the future, there's still a lot to do, not necessarily studying more nearby clusters, but really looking at the data in a different way. And you can do this with machine learning in clusters of galaxies. There have been some studies so far that have looked at images of clusters in the X-rays. And when you do this, you can get constraints on cluster masses or cool core properties. And I invite you to look up these papers here. There's also going to be a talk right after Florence's talk on illustrious TNG. So stay tuned for that. But you can also, in addition to applying machine learning techniques to images, you can also do this for spectra. And this is a study that Ray et al. Did in 2020. And this is the last point I want to make. So what you can do is you can also apply machine learning techniques to X-ray spectra of galaxy clusters. And one of the key problems that we know is essentially if you look at a cluster and you look at its core, if you extract a spectrum, an X-ray spectrum from the core, we know that this spectrum can be fit with one temperature component, but that often in the cluster cores, at least in X-ray wavelengths, there's evidence that there are multiple temperatures, plasma multiple temperatures in these regions. And the question is, how do you determine if your spectra is better fit with one temperature or two temperature or three? And you can do this with traditional techniques that look at the reduced chi-square fit to constrain this. But there's no systematic way of doing this properly. Whereas you can also address the same problem with machine learning. And what I'm showing here is called a confusion matrix. This is the last slide. I just want to highlight here some results. So this is the true number of temperature components versus what the machine learning algorithm predicts. And what you see is that in general, for one true temperature component, the algorithm can do a very good job at predicting quantitatively and robustly the number of components. And what's really great about these machine learning techniques is that they can be applied to any kind of data, any kind of X-ray or other wavelengths data. It's very versatile, and they're extremely quick, and they perform much better than traditional methods in low signal to noise regions. So I think this is where the future is, especially revisiting nearby clusters, but using more sophisticated techniques to analyze the data. And that's the review. I would have loved to talk about other topics. There's so many things to say about local nearby clusters, but I'm looking forward to the other talks.